If you take two molecules of ammonia and join them together through the nitrogens, you get hydrazine, which is a highly flammable and toxic substance that's used as rocket fuel. And if you put organic groups onto one or both of the nitrogens, you get organic hydrazines, which are generally less reactive and hazardous than hydrazine itself, but still useful and nasty in their own ways. Phenylhydrazine, with a benzene ring attached to one of the nitrogens, was the very first hydrazine derivative to be prepared. It was originally prepared and characterised in 1875 by German chemist Emil Fischer, who found it could be used to identify reducing sugars, as it reacts with them to form characteristic highly insoluble crystalline compounds known as osazones, which was a very useful diagnostic tool in the times before NMR. It's also used to prepare indole derivatives by condensation with carbonyl compounds, a reaction that was developed and pioneered by Emil Fischer. It's fair to say this is very much Emil Fischer's signature molecule. The key step in the indole synthesis is a 3,3 sigmatropic rearrangement, but this was only understood following the advent of quantum mechanics and its application to chemistry, both of which happened many years after Fischer's death in 1919. A number of indole derivatives are naturally occurring psychoactive compounds, including serotonin, melatonin, and this stuff. The procedure I used to make phenylhydrazine is from 1922 and is based on Fischer's original synthesis. I've included some refinements, partly based on a 1962 Hoechst patent for the industrial synthesis, and partly based on my own experimentation. Links to both sources can be found in the description. In this synthesis, aniline is converted to its diazonium salt by nitrous acid, then reduced to phenylhydrazine with sodium sulfite and sodium bisulfite, and converted to its hydrochloride salt with a large excess of hydrochloric acid. Every amateur chemist and their dog has got a video about making hydrazine, but the only other video I've found actually demonstrating a phenylhydrazine synthesis is by Niall Red. He used a similar method to this, but instead of sulfite he used a dissolving metal reduction with tin to reduce the diazonium salt to the hydrazine. This procedure also had some personal significance for me because although I learned all about diazotization reactions 20 odd years ago at A level and at university, I'd never actually done one until now. The procedure was carried out at a scale of 1/10 of a mole. The reagents used were aniline, 37% hydrochloric acid, sodium nitrite, sodium sulfite, sodium metabisulfite, a bit of THF, a whole load of deionized water, and plenty of ice. So 22.5 grams of 37% hydrochloric acid was added to 50 ml of deionized water, then 9.3 grams of aniline was added slowly and carefully and mixed until uniform. This caused the mixture to heat up. You can't see this at all on camera, but the temperature jumped from about 15 to nearly 40 degrees. This solution was cooled to around 4 degrees in the fridge. I left it in there overnight. 6.9 grams of sodium nitrate was dissolved in deionized water, which is 15 ml of that, and this solution was cooled in the fridge as well. Now, at this point, the 1922 procedure calls for a sodium sulfite solution to be prepared by bubbling sulfur dioxide gas through a caustic soda solution on the grounds that the reagent-grade sodium sulfite available at the time was not sufficiently pure. Since that's no longer true, this step is not necessary and the solution can be made directly from sodium sulfite. Also, the end result is described as being a sulfite solution, but in reality it's a mixture of sulfite and bisulfite. Sulfite is formed by a molecule of hydroxide adding to sulfur dioxide, then being deprotonated by another molecule of hydroxide, but as the amount of caustic soda runs low, the initial addition products are not deprotonated, resulting in bisulfite. The Hoechst patent described using a formulated mixture of the two to achieve the correct pH for the reaction without any need for the pH adjustment called for in the 1922 procedure, and I found from experiment that a 3 to 2 molar mixture of sulfite and bisulfite works best. So with that in mind, 23.6 grams of sodium sulfite and 13.5 grams of sodium metabisulfite were dissolved in 150 ml of deionized water, then cooled overnight in the fridge. One thing worth noting is that sodium sulfite, much like its more oxidized cousin sodium sulfate, has a tendency to form hard compacted crusts that are slow to dissolve. Vigorous stirring, gentle heating and poking them with a sharp end of a spatula are all good ways to break them up. The pH of the final mixture should be about 6, and this will decrease slightly during the reaction as you're adding an acidic solution to it. The Hoechst pattern claims the ideal pH of the reaction is between 5 and 6. Once the aniline hydrochloride solution was cool enough, it was placed in an ice salt bath, and the nitrite solution was added to it slowly and carefully with stirring, because the reaction is pretty exothermic. The temperature was monitored throughout to make sure it didn't go above about 6 degrees, or 8 degrees at the very most. If it gets too warm, it'll start gently bubbling, which is the diazonium salt self-destructing and releasing nitrogen, which you really don't want. You'll need to go very slowly at first, and you'll probably need to add some ice to the beaker. You don't strictly need an addition funnel, but it allows you to add the nitrite solution at a much slower rate than manually dripping it in using a pipette, which is a process that would test the patience of most saints. After the nitrite solution was added, the mixture was dumped into the sulfite solution, causing it to turn a truly spectacular shade of bright red and become opaque. The mixture was heated to about 80 degrees and mixed for 3 hours. Over the first hour or two, the colour slowly faded from Tizer red to iron brew style orange and then to peach scented toiletry style orange. The smell, however, was anything but peachy. Besides the slight whiff of sulphur dioxide you get when boiling mildly acidic sulfite solutions, the phenylhydrazine itself could be smelt, and it's got quite a different smell to aniline. Aniline smells like fishy petrol, while phenylhydrazine has more of a disinfectant mothball type smell. It's funny how much difference an extra nitrogen makes. So 40 grams of 37% hydrochloric acid was added to the mixture in portions to neutralise the sulfites, turn our product to its hydrochloride salt and precipitate it by flooding the solution with chloride ions. I have tried this with sodium and ammonium chloride, but neither are quite as effective, and both of them precipitate out inorganic salts as well as the product, meaning that you're then lumbered with the dour task of separating them. As you can see, a huge amount of solid material precipitated out. The mixture was cooled to room temperature, at which it resembled some kind of weird iridescent pinky peach toxic smoothie that reeked of hydrochloric acid. The precipitate was collected by vacuum filtration. To remove the water-soluble impurities, I washed it with 10% hydrochloric acid and a little THF. THF was particularly effective at removing the pink-orange impurity, which was most likely an azo compound of some kind. Normally I'd use alcohol or acetone for this purpose, but the product is highly soluble alcohol, and it reacts with acetone to form a phenylhydrazine, so neither of them can be used here. Even after a lengthy spell on the pump, it was clear that a lot of water was still entrained in the product, and the force of vacuum alone was not enough to remove it. I transferred the wet paste to a round bottom flask and heated it under vacuum, with a silica gel trap placed in between the flask and the vacuum inlet to catch the water. This is the way I typically dry hygroscopic compounds. Phenylhydrazine hydrochloride is generally very soluble in water, but it becomes very insoluble when said water has been spammed with chloride ions. Vacuum distillation removed the vast majority of the water, and the last little bit was removed by flame drying, yielding 8.8 grams of phenylhydrazine hydrochloride as an off-white, nearly colourless, free-flowing powder representing a yield of 61% with respect to aniline. Which is not bad, though it could be improved. The purity could have been improved by recrystallization, but it was getting late and this product was good enough as a synthetic intermediate. Well, that was something pretty close to the original method for making a phenylhydrazine. The 1922 method, which was done on a near kilogram scale, involved isolating it as a free base, extracting it with benzene and distilling it, which I felt was not strictly necessary at this scale. To the best of my knowledge, the modern industrial process is not much different, other than the fact it's continuous rather than batch-based, and it's more efficient than this. I hope you enjoyed this video. Thank you for watching.